All right. So this is now the last part. Actually, it's just an outlook. So I'm just going to kind of drive you through what we've been doing very, very quickly in terms of material to refresh a little bit. Then I'll give you a bit of an outlook to big data for engineers if some of you want to come back in the spring for the most recent developments of databases. So you remember that's actually a common mistake that many people make. A database is the data itself, right? A clay tablet is a database, right? What's on the database? It's the data. Then you have the database management system that is PostgreSQL. That is all the software that the engineers have written in C++ or in Java to handle all of the physical details for you. This is called the database management system. And the two together, the data plus the software, is the database system. Okay? So you need to always remember that the database is the data itself. A lot of people make that mistake. They basically say that PostgreSQL is a database. No, PostgreSQL is not a database. It's a database management system. Okay? Then, data independence. We saw that this is this extremely important principle that shields the user from the details. And it's true for tables, but in big data for engineers, we see it's also true for trees, for graphs, for cubes, for many other shapes. Well, for cubes, we saw it here already. And everything is eventually written to physical storage. Now I've shown it. The physical storage, you've seen it just a few minutes ago. That was the chunks and the pages and so on that PostgreSQL is writing and that the user doesn't need to care about. What's really nice about data independence is that you can change that. In big data for engineers, we see that you can, instead of PostgreSQL and all of these chunks and pages and so on, instead you could use a data center and you could use file systems that are distributed and Spark and MapReduce and all kinds of other things. You can actually change that to something else without changing that. That remains the same, right? That's really the logical level. That is data independence. Then we looked mathematically into the relational model. We saw that a relational table or a relation is a set of maps where the maps map attributes to values. Here it's a set of 3 maps. And we furthermore saw that this set of maps needs to fulfill 3 things. Relational integrity, the maps must have the same attributes. They all must have last first physicist year so that you can glue them to a table. Domain integrity, it means that for the same attribute, it's the same types. Year, for example, must always be an integer, physicist a Boolean, first and last some string. And third, atomic integrity, also called first normal form, where every value is atomic. No nested objects, nested array, nested tables, and so on. That's forbidden. And that's a relational table, right? A set of maps. Of course, we saw that you can also have lists of maps or bags of maps. That's different flavors. Then it depends on whether you care about the order of the records, and it depends if you want to allow for duplicate records if they repeat. Okay. Then we looked into the actual types. So of course, mathematically, types are just sets, the sets of the values that you accept within a column. But when you have a database management system that has a language like SQL, it has a few types that are called built-in. Built-in means that they are predefined and you can just go ahead and use them. So it's like this restaurant menu that I've shown you, where you have a few types for storing characters and strings, some binary types for storing images, videos, and so on. Then you have these numbers. So you have, small int, integer, big int if you want integers, and you have numeric and decimal, which are they mean the same thing for when you have a point in the middle and you want to have decimal numbers. Then you have approximate real numbers, where we have this IEEE 754 way of storing a number in scientific notation. And what's actually stored is basically the power of 10 plus the mantissa, so the actual digits. And so here you also have types for that. Plenty of different names: float, real, double precision. Then you can store Boolean types. Then you have dates, times, timestamps, with or without time zone. You have intervals, for example, 2 years and 3 months, or 1 day and 4 hours, 3 minutes and 14 seconds. So that's this big menu that you have in the system. Now, I warned you that the names of the types can vary. There is a SQL standard, of course, that everybody should implement, but everybody doesn't actually implement exactly as it is. So in fact, in the real world, every database management system slightly deviates from SQL. And so you should not be surprised if the exact types are going to change between the systems. But nothing to worry about. It's still going to be more or less the same types. They just have different names. It's just like traveling to another canton, and then they use a different word like Embly and Embruf instead of, in some cantons. So it's just a different dialect. You just need to look up the documentation. By the way, on exam day, you'll have the documentation. We'll include PostgreSQL documentation. All right. And we take, by the way, PostgreSQL in this course because it's one of the closest to the SQL standard. If you take other implementations like IBM, Microsoft, and so on, they are a bit further away. So PostgreSQL is great for teaching in this aspect. Okay. Then we saw that now we have defined the tables and the types and the schemas and so on. We can manipulate them. We can create tables, we can modify the tables, we can populate the tables by inserting or removing tuples. We can drop the tables completely. And I showed you the commands, right? In SQL, it's create table, drop table, and so on. So that's at the level of a table, right? Create a table, modify a table, drop a table. By modify a table, we mean you add a column, you remove a column, you change the path. For example, you make a column null instead of not null, or you add a constraint, like these kind of things. The default value of a column you can change. And then you have at the tuple level, when you insert or delete or update tuples or query tuples. And this is known as data manipulation language, while if you work at the table level, it's called data definition language. Right? All right, and so this is on the high level, and I've shown you the SQL for that, right? I've shown you all of the SQL instructions. I've also shown you how we can connect the tables to each other. This is called a join. And when we do that, it's very common that a join is made on a foreign key and a primary key. It means that a table points to another table. For example, you could have a list of tax residencies, and in order to identify a person, you use the AHFAO number. And for this, that's a foreign key that points to the table of persons where the AHFAO defines the person. So in the table persons, that's a primary key. And you see how the foreign key points to the primary key. That's a very natural thing to do in a database. And then we can join in this way. We also saw the link with normal forms is that when you have a normal form, it precisely means doing that sort of things. When you have a normal form, you want to split your big table into several smaller tables where every small table does just one thing, persons, tax residencies, and so on. And then you relate them like this with a join. Okay. Then we saw that when you actually go ahead and query the data, mathematically, that's the relational algebra. In practice, that's going to be with the SQL language. We saw that there's all kinds of primitives that you can use. Unions, intersection, subtraction of tables, that's the set queries. Very natural if you see a table as a set of maps. You can manipulate the sets. You can filter on the rows or on the columns. So the selection filters columns, the selection filters rows, the projection filters columns. Then you can rename the whole relation or the attributes in a table. Then you can group, aggregate the data, or you can sort the data. But that, of course, only works if you have lists of maps. If you have sets of maps, there's no order. Why did I call them shuffling queries? That you will know in big data for engineers. Because actually, if you want to implement grouping and sorting, that involves something called shuffling in the data center. I also call that spaghetti, the shuffling. But that I'm keeping for spring. And joining queries is when you have multiple tables involved. Cartesian product is the brute force one that maps every record of one table to every other record of the table. And this is the one that's going to crash your machine. So again, a word of warning, on exam day, do not do Cartesian products. Be very, very careful. That is the way to crash the computer. Instead of the Cartesian product, you should add some filter on the Cartesian product. And when you do filter the Cartesian product, that's called the join. right? Because you only want to associate tuples that match. An example of tuple that match is here. A join will only associate the alpha that ends with 1 to 4 with the exact same over here, right? So this is not the whole Cartesian product. It's only the tuples that match, right? And that's what we call joins. Natural join is when you match the columns with the same name. Theta join is the more generic one where you manually specify how tuples are going to match with predicates. Okay. So visually, this is what a join looks like. You see that the whole Cartesian product of these two would be 2 times 3, so it would have 6. But because it's a join, we don't have all 6 combinations. We only associate A with A and B with B. So for A, you have 2 ways, with the first one and the third one of the table on the right. And B, you only have 1 way, right? So that gives you 3 tuples. So that's joining. Then you have grouping, where you put in groups all of the records that have the same values, and then you aggregate with a sum, a count, a mean, a max, or an average. And finally, you have sorting. So just so that you have this impression, selection, projection is actually quite efficient. Selection and projection, even on petabytes of data in a data center, this is something that the complexity is quite acceptable. This is something we like. It's basically linear. These are the tough ones. Grouping and sorting, these are the ones that, because they involve this shuffling, a lot of data has to flow around. And these ones are not in linear time. This is more like n log n, if you know the complexity, so it takes more time. So remember, joining, grouping, and sorting are generally more expensive. Selection, projection are usually cheaper in complexity. Okay? Then we saw that for the benefit of data independence, we like to have a query language that is declarative, like SQL, with this select from where and so on, where you just state what you want. You don't need to worry about how efficient that is. You just leave it to the system. And then you have imperative languages that tell the computer exactly what to do. So in imperative language, we'll have features like variable assignments, while loops, iterations, and so on. So that's all things you have in an imperative language. You also can have side effects. Side effects, that's the name that computer scientists use when you see a change, when you modify something. For example, if you execute a computer program and that changes a file, that is a side effect. I can show you a side effect concretely. Like if I push the button, that's a side effect, right? That's a side effect. And so only imperative languages are supposed to have that. In a declarative language, you just state what you want. And again, I insist, the user of PostgreSQL is here. They just write in a declarative way. This here is inside PostgreSQL, well hidden, but PostgreSQL is written in an imperative language. All right, I think didn't get the light right when I switched it back on. I have a way of switching off these two on the front. All right. Okay, so now on the SQL side, this is a reminder that in SQL, the order of the clauses is fixed. It's always the same. Select, from, where, group by, having, order by, limit of sets. They are optional, right? So select and from, you need them, but where, group by, having, order by, limit of set, they're all optional. You may or may not have them. But it has to be in that order. You cannot change the order. So you have learn it by heart, the order. Then you're going to be fine. All right. And then, of course, inside the from clause, you might have some more complex stuff. If you want to do joins or involve multiple tables, then you have a lot of action inside the from clause. An example is a join, full outer join with a predicate, so that we've all covered. Okay. Then, after doing that, teaching you how to query tables in a declarative way, I introduced you to a more advanced part called database design theory. And database design theory is just a lot of heavy math, the purpose of which is to do good schemas, to create a structure in your database that works nicely. And works nicely means you don't run into problems such as inconsistencies in the data, and it remains with good performance. And so the take-home message, the main take-home message of database design theories is that we like for our data to be in higher normal forms. And a higher normal forms basically means more smaller tables. A lower normal forms means fewer larger tables, right? So we saw there's a first normal form, second, third, Boyce code 3.5. There's a fourth, a fifth, a sixth normal form. But we mostly focused on the Boyce code normal form and on the first normal form, which is the atomic values. All right, and so in a good system, you have each table does its thing, and then they relate with these foreign keys and primary keys. All right, and so in order to do that, we saw that we can have constraints on the tables. One of these constraints is called the functional dependency. So the functional dependencies, they're just a mathematical tool that is used in the definition of the normal forms. And so having a functional dependency means that some columns imply the values of some others. For example, if here you have the same values for A and B, then you must have the same values for D and E. It means that D and E are a function of A and B, right? That's a functional dependency. And the functional dependencies are expressed like this, where you have on the left what implies and on the right what is implied. So here, basically, it means that C is a function of A. In other words, if you know A, then you know C. And of course, you can have multiple as well. So here it means if you know A and B, then you know C. Then you can have multiple functional dependencies that basically constrain what the data can look like. And we saw a whole lot of things that we can do with that. We can compute a closure of a set of attributes. That's the one question that 100% of you got right when we did it. It's just a game where you try to add as many as you can whenever based on the rules from the left. So that's called the closure of a set of attributes. Basically means everything you know if you know A and B, right? Then we saw that because we're in Switzerland, we like to clean up things. So when you have a set of functional dependencies, you can clean it up and tidy it all up in what's called a minimal basis. Careful, there can be more than one minimal basis. Like there's many ways to tidy up the same room. That's another way of putting it, okay? Then we saw the Boyce code normal form. The Boyce code normal form is the one of the easiest to understand. So this is why I focused on that one. The general idea of normal forms is we do not like functional dependencies, or some functional dependencies are undesirable. And in the case of the Boyce code normal form, we do not like functional dependencies if what's on the left is not a super key, right? We only like functional dependencies that have super keys on the left. Remember that a super key is a set of attributes that functionally determines the whole table. So if you know these attributes in the super key, then you know all of them. And whenever you have a functional dependency and the left is not super key, it doesn't determine the whole table, then we don't like that, and it's not in the Boyce code normal form, right? Then we saw that if we have a table that is not in the Boyce code normal form, we can try to split it into multiple tables that would be in Boyce code normal form. And we saw that that works. I gave you an algorithm for doing that. You can decompose the table based on a functional dependency that breaks the rule, that has something that's not a super key on the left. And we saw that we can do it in a lossless fashion. Lossless means that these split tables are exactly the same thing as the original table. That's the same information. You can go between them, it's exactly the same thing. So lossless. No update anomalies, meaning that you don't run into the issues that you have redundancy and so on. But we saw that for Boyce code, you might lose some of the dependencies, some of the functional dependencies. So that's this impossibility triangle that we have. All right. What else did we look like? This is the secret of a web shop. When you have a website and you look for products and you place your orders, they typically have a database in the background. And this is made in 3 layers. You have the layer of the web server. These are the ones that deliver the HTML pages and the pictures. Then you have the application servers. They have what's called the business logic. It's a lot of complex code in PHP, Java, C++, typically an imperative language that generates the HTML that the web servers are going to deliver. And in order to do that, this business logic has to communicate with the database because it has to look at the data. And when you look at the data, you don't do it directly because of data independence. Instead, you communicate with PostgreSQL using SQL. And PostgreSQL, the database server, will take care of reading the data from disk and delivering it to you. We've looked a little bit at how it looks like when you have this interface. Then we saw that thanks to data independence, in SQL, you say select from where a certain equality holds. And we saw that by using indices, we can cheat and make it faster. So an index is exactly what you have at the end of a book when you have the alphabetical list of words that directly points to the page numbers where you can find them. And we saw tree indices and hash indices. So that would be something like a tree index that accelerates the search. And we saw that with a tree index, you can look up a record in logarithmic time. And the intuition behind logarithmic is that only the places that have a color are actually accessed. Everything that is not colored is not. And so this is much less than the whole data. It's a logarithm. It's in the logarithm of the whole data size. Okay. And a hash index is even better than logarithmic. It's instant. In a hash index, you snap your fingers and you immediately access the value. Of course, there's a price for that. It takes space. There's always a price to pay for this. All right, then we saw that data can have structure or less or more structures. In this course, we focused on the structured data, so tables and something that is even more structured than a table is a cube, and that we didn't touch. This is all for big data for engineers. So we saw that this is structured data. So what's even more structured than the tables is the cubes. We saw that you can visualize a cube with slicing and dicing. That would be the pivot table feature in a spreadsheet software, where you put a fact table that you import as a CSV, and then you drag and drop salesperson over here, domain period over here, that would be period. Then you drag and drop the slicers. You say, okay, I want Switzerland, I want US dollars, and the spreadsheet is magically going to display it in here. Right, so this is called a pivot table or cross tabulation. We saw that we can store that in a relational database management system, that typically what we store is a facts table where every column is a dimension except the last one that has the value. We saw that you can have all kinds. If you love normal forms, you can have a star schema or even a snowflake schema where these satellite tables around the fact table contain more information. We saw that you can also denormalize that all by joining everything, and this is what you get. You get a single big table that obviously then is not in a high normal form. That's the sort of tables you can import directly in a spreadsheet software to pivot on. Finally, we saw that out of this, we can use SQL to extract the data we need in order to put it in a view like this, right? So that was an example of query thanks to an extension of SQL that PostgreSQL has, grouped by cube, that allows you to extract the data and compute the data that you need in order to create a view like that. So in that case, the SQL computed the 20, the 14, the 11, 14, 9, and 34, but was all computed by this SQL query with a group by cube, right? And then we saw that we can also have group by rollup. So the group by rollup, it's in order to get the data to generate a view like that, where you have a whole hierarchy of subtotals and subtotals and subtotals all the way up to a grand total, right? So months, quarters, years, and then all times. All right. And finally, and that's actually today, it's still fresh. When you actually implement that, you need to deal with hardware. It means the actual place where you store the data and all the electronics that computes the output data, right? So it's a good idea for you, even you don't need to know too many details, but be aware that there is this hierarchy here with the CPU cache, the working memory, the RAM, the disk, SSDs or HDDs, and then the tapes. The higher you get, the more expensive it is, and the faster it is. The lower you get, the cheaper it gets, but also the more capacity you have. All right, so that was a very quick wrap-up of the material. I included a few slides, so thank you, by the way, for filling the course evaluation. this is very useful to get feedback and also to know what we can improve for later. So I have put everything. You can look offline at the site. So these are all the questions that you had to answer. So of course, I'm happy to see that you understood what I've been telling you for 14 weeks. That's the best thing that a teacher can ever hear. So the goal for these questions is to be as much as possible to the right. So the assistants also did a great job. So thank you. Andreas and everybody else in the TA team. Hopefully a few will come in the second hour. We want them to play against you. And so here the goal for the two questions in the middle is to be in the middle, right? So this is the knowledge required for the lecture. Was it too much or not enough? So here you want to be as close as possible to here. And then that's the effort compared to other courses. So this is basically al dente is right here. Okay. So we'll take a break. I'll tell you a little bit about the exam. I'll give you a bit of an outlook to big data. We'll proceed with the quiz and decide who of you is going to get the trophy, and also a few sweets as well go with the trophy. All right, so take a good break. I'll see you in 15 minutes for